Hello everyone, I'm Fernando, and today I will talk about our paper, Fusion of Operators of Computational Graphs by a Greedy Clustering, the XNNC experience. So this is an experience paper that tells the story of work that ended up being used on a real-world compiler with XNNC. And the goal of this work is to design and implement a new kernel fusion algorithm. I will explain what kernel fusion is shortly. And we want to deploy this algorithm on the XNNC compiler. And again, it is an experience paper. It will tell this story. XNNC stands for Xtensa Neural Network Compiler. So this is a tool used by Cadence, by the Tensilica branch of Cadence, to generate code for convolutional neural networks. In particular, it will convert those convolutional neural networks that may be designed with floating point numbers in mind to machine code that's optimized and used like integers to carry out those operations. So it does some quantization. And the code that it produces will run on usually digital signal processors, like those that we find in like vehicle networks, lidar systems, consumer electronics, appliances, etc. And XNNC is implemented in C++. It's a relatively large project, although much smaller than GCC or LLVM. It still has 1.5 million lines of code. It uses LLVM, a little bit of it. In particular, it uses some MLIR dialects. And it was implemented originally in Austin, and nowadays it's still implemented partially in Austin, but part of the implementation team moved to Belo Horizonte, which is the city where UFMG, my university, is located. So just last year, they hired 5 of our graduate students to work there on this AI compiler. And that's an example of a success story where a company funds research in a university and gets back highly qualified professionals. So let's get back into XNNC, and it does, it converts floating point CNNs into fixed point optimized machine code. A convolutional neural network can be represented as a computational graph where vertices, they are what we call kernels. So they implement some operation like matrix multiplication, convolution, ReLU, transposition, and such. And then the edges in this graph, they denote the way that the data flows, from one kernel to the next one. And then what XNNC does is to convert these to some code, like I'm going to show an example here, that more or less looks like C++, where kernels, they will be represented by function calls. Sometimes the pre-built kernel library of XNNC will not have a particular kernel already pre-made, and then it will have to generate some gluing code that we can use to implement the neural network. And then it will translate this C++ code into machine code that will run on some embedded device like a digital signal processor, as I mentioned before. So XNNC, again, is like what we call a Tensor compiler, an AI compiler. Something that I find interesting in this world is that we do have an instruction selection phase, but it applies on the computational graph. That's in contrast to a traditional compiler where our instruction selection will do pattern matching on the AST, and we'll convert AST nodes, or maybe higher level IR nodes like the LVM IR, into instructions. In the Tensor compiler, we shall be converting nodes of the computational graph into kernels and loops that may put these kernels together. But what's operator fusion? That's a compiler transformation. It's pretty old. It has been present in Allen's and Koch catalog of optimizing transformations in 1971. So here we have two Nobel laureates. So that's an old compiler optimization. I will show how it works in the context of a neural network. And for that, I shall use this operator here, a single head attention. So that sits at the core of the transformer architecture. It was introduced in that paper by Vaswani. The attention is all you need paper that became very famous in the context of machine learning. Anyways, we can describe single head attention as this formula that involves function softmax and then two vector multiplications and then one transposition, and then there is a square root of a scalar d here. Anyways, we can represent this formula as this computational graph where we have matrices k, q, and v and one scalar h. And then we have the kernels in the middle, like transpose, mul, div, softmax, mul again. So these are kernels. Let's look into the PyTorch implementation of this network. Here we have it, like with 3 lines of code. Let's focus on the first line. So we have two operators, like matmul and transpose. Now, let's imagine that in our library of kernels, we have one that actually combines these two. So we could like replace these two kernels with a new one that's the fused version of matmul and transpose. So that's fusion in this context. So before we had two kernel calls, and now we have only one. And this fusion is very advantageous because before we had to read two tensors, k and q, and still have to read only two tensors, again, k and q. But now let's imagine that in our library we have one kernel that implements fused attention, like attention. And then we can fuse the whole thing, you know. And indeed it is, we can import this kernel. So now we have a situation where we need to keep 3 tensors in memory, 3 matrices in memory, k, q, and v. So if we have a memory hierarchy, this may not be very profitable. So typically these machine architectures, they have like fast memory and slow memory. The tensors, they will fit into the slow memory because even though it's low, it's plenty. But we need to operate on those tensors by bringing them into the fast memory. And depending on how much data we have, we may not be able to fit all the tensors that we need into the fast memory. And in this case, there'll be thrashing. You have to go back and forth in between the fast and the slow memory. Anyway, so this brings us to our first observation. Fusion improves performance, but not always. And deciding which operators to fuse is a very challenging problem. Why it's challenging? Well, because a neural network can be represented by a very large graph. I mean, this is a small network, but we could have thousands of operators and more thousands of edges connecting them. So that brings us to the key question, like which operators does it make sense to fuse? Well, first we need to fuse operators. We can fuse operators, or we should fuse operators that are related by a producer-consumer relation. Like in this example here, we have that the first operator produces a matrix C that the second operator consumes. So it would make sense to fuse them. But we have to remember that fusion boils down to combining loops. So ideally, we should fuse loops that range on the same dimensions. what's the case here, right? We have like the same trip counts. So you could fuse these two outermost loops. And then we have like a fuse operator, but this time we may need more space to store the data, because now we're receiving and reading 3 matrices at a time, whereas before we're reading at most 2. And that brings us to our third observation. Fusion, when seen as an optimization problem, is guided by a cost model. So a cost model can be like something that we obtain via profiling. We profile the network and then we decide if fusion was good or not. But it can be static as well. So we can derive equations that will estimate the cost of running a network. So a static cost model is a function that maps a program to an estimation of its running time. There are many cost models in the literature. For instance, here is the one that I took from this paper published in PLTI 2021 by Fabrice's group. So that's what the surfaces that we obtain by varying dimensions of tiling. So we're doing tiling, and then we can choose different tiling windows. So that's what we get. And here is another cost model. This one is from Cadence. So whereas the previous one is convex, this one, it doesn't really it cannot be described by a convex surface. It's full of bumps, local minimum. This cost model, it doesn't really come from an equation. It's produced by traversing a data structure and then computing particular costs of the nodes of that data structure. So here again, we're comparing like different sizes of the tiling window. So we vary those sizes, we traverse this data structure, and then we get the points that form the surface. The y-axis here is the estimated performance. Okay, and this data structure, it comes from a program. So we have a program, we derive a data structure from this program, we traverse this data structure with certain parameters, and then we get the cost model. This cost model is very accurate. If you compare like the estimates with the simulated cost, we more or less get like a very strong relation, very strong linear relation. Anyway, so back into fusion. Now we have this optimization problem. We have a graph full of fusion possibilities, and we need to decide which possibilities we take in. So we need to minimize the cost that's associated with this fusion operations. So there are many ways of solving this optimization problem. We can use exhaustive algorithms, like the one that was presented by Kai et al. In 2023. We can use an evolutionary approach, like the one that we find in TVM, like in Tensor, that was presented in 2020. Or we can use something that we shall call the minimum spanning tree algorithm. That's the core of this paper. So this is what we shall be presenting in this paper. So let me show how that works. So this is a greedy algorithm guided by a cost model. It groups nodes into clusters, and then at any given point, it will choose the 2 most profitable clusters and will fuse them together until no more fusions are possible. So it keeps a queue of priorities, and then in that queue, we have the pairs of clusters that we can fuse. And by most profitable, I mean that reduces the overall cost of the computational graph the most. So just as an example, let's assume that we have a graph like this. And then we have a cost model. So this cost model will assign costs to edges and to vertices. So we can think of the cost of an edge as the cost of transferring data, and the cost of a vertex as the cost of computing that vertex. There are some properties, or rather anti-properties that we have here. First, fusion is is non-associative. So I mean, if I fuse A with B and C, if I fuse A with B and then fuse the corresponding node with C, or if I fuse B with C and then the corresponding node, I fuse that with A, that doesn't really gives us the same cost, not guaranteed to give the same cost. Because I mean, essentially the cost is derived from code, and the compiler may generate code in different ways for those combinations. And there is not really a matroid structure, meaning that we can't really use local decisions to find the optimal solution to the fusion problem. So I mean, a greedy algorithm wouldn't work in this case. So continuing with our example, let's assume that we can fuse, but accept that the cost of all the incoming and outgoing edges can never be above 5. I mean, if you fuse two nodes, we have to make sure that the sum of incoming and outgoing edges is less than 5. That's just to assume that memory capacity is at most 4. So, and we can assume that fusion is homomorphic with regard to the cost, meaning that, you know, the cost of node A plus the cost of node B is the cost of the fused node. And we can assume also that once you fuse two nodes, the cost of the edge that links those nodes is 0, okay? So here we have 5 examples, 5 clusters that could fuse, 5 candidates. And then we ask ourselves, what's the most profitable fusion? We have to see which one would reduce the cost the most. We have that this is the cost of the edges plus the cost of the vertices. And in this case, fusing A and B is the most profitable alternative. So I mean, we continue like this. So we have to see like what would be the fusion that would reduce the overall cost the most, and we see that fusing A, B, and C would yield the best cost at this point. And then after this point, no more fusions are possible, and we're done. So I mean, that's again a very simple algorithm, but it's very effective, as I will show. So how good is this cluster-based approach? We ran like a number of experiments, so I'm going to show you some results here. We have 19 benchmarks. They are all implementations of convolutional neural networks in the ONNX format. And then they all receive the same image, which is like a relatively small image, but they all receive the same image. And we shall be reporting results here in terms of number of cycles. So this number of cycles is computed using the Xtensa Explorer simulator. So it is a cycle accurate simulator. And we shall be using in this experiment here one processor from Tensilica, the P6, but in the paper we use a few more. So we have like 5 approaches here, 5 fusion approaches. Well, maybe the first is not really a fusion approach, I mean, it's no fusion. And then have DFS, which was the original algorithm used in the XNNC compiler. So, I mean, there are details of this algorithm in the paper. And then have MST, which is the algorithm that I just explained before. And then we have EVL, that's an evolutionary algorithm that we implemented after the implementation that we got into TVM. And then have PKT, which is what we call the backtracking approach. I mean, it is an exhaustive algorithm that will try every possible way of using the nodes and we'll keep the best result. So these are the results that we got. It's a lot of bars, but we can go over them slowly. So first, I mean, blue is no fusion. And then, as you see, I mean, regardless of the approach, we are always improving upon blue. Okay. And then, like red is the original algorithm of XNNC. And all the new algorithms, they improve upon the DFS approach. So, I mean, for instance, our proposed algorithm, MST, is like yields overall kernels, like which are 39% faster on average. And then BKT, like the black bars, they they're not always better. I mean, there was a lot of timeout. So, I mean, I think past ResNet 34, we always get some timeout. I mean, the models here, they're sorted on the x-axis by size, measured in terms of number of edges of the computational graph. So, I mean, after ResNet 34, there will be timeouts for BKT. And then we don't really see any statistical difference between the quality of the kernels that MST and EVL produce, except that MST is much faster and is much simpler as well. I mean, the implementation is much smaller. So if you compare like the compilation time using those different algorithms, we see that they're more or less similar, except that PKT, I mean, it couldn't really terminate in many of our models. So I think like this exhaustive approach, it wouldn't be practical in the context of XNNC. Anyways, our algorithm is about 25% faster than MST, than AVL, but produces kernels with the same quality. So again, we have a faster algorithm that's equally as good than AVL. Our algorithm is a bit slower than DFS, 11% slower, but generates code that's 39% faster. The implementation of MST is a bit larger than the implementation of DFS, but not by much, and is much shorter than the implementation of EVL, the evolutionary approach. The exhaustive approach, it seems to be impractical, at least in the context of XNNC, because we have like large models, like with thousands of operators and thousands of edges. And if you want to know more about these algorithms, I invite you to read the paper. And that's it. Thank you very much for your time.